Continuing on with our discussion of fluids topics, I will be discussing my own problems for topics 5 through 12. Here, we are given a situation where in the 1950s water tanks were stored at the top of skyscrapers and a fire breaks out. We are given the knowns of the length of the pipe, inner diameter, the loss coefficient of a sharp-edged inlet, smooth-edged 90-degree elbow. We are also given the volumetric flow rate, density, mu, and the PV, the roughness, and the Z1 minus Z2, the differences in points 1 and 2 height, in addition to the pressure. We want to find Z1 at cavitation, given the properties. We are assuming steady state, incompressible flow, and fully developed flow with no work. We will be using here the extended Bernoulli equation, Reynolds number, friction losses for laminar and turbulent, and head loss along with net PSH. Here, we will set up the equation and write down the equation for MPSH, which is given here. We are assuming that the velocity of point 1 is negligible. Using Bernoulli, we are able to cancel out the following terms, as we are able to cancel out V1, the H of the pump, and the H of the turbine. Notice, we are able to cancel out the H of the pump because point 2 is right before the entrance of the pump. Simplifying, we are able to get that P2 over rho g is equal to the following. Now, we are able to substitute and assume that PS is equal to P2 as stated here in this equation. Subbing this in, we are then able to get the equation for the MPSH. Using the equation for Reynolds numbers, which is rho VD, the F prime for friction losses, which is for turbulent flow after we determine for the Reynolds number, we are then able to determine the head loss. After this, we are able to plug into our equation in order to determine the net positive suction head at the pump, which is 9.63 meters at cavitation. Now, for part B, we are to state the Reynolds number boundaries for laminar and turbulent flow, their key friction factor equations, and the physical differences. Here, we show that laminar's friction factor coefficient equation is 16 over Re, and that Reynolds numbers are less than 2300. For turbulent flow, we use that the friction factor is equal to the following equation, with typical Reynolds numbers greater than 10,000. Laminar flow is characterized by smooth, uniform fluid flow, and turbulent flow is characterized by the irregular movement of particles in the fluid. Continuing on our discussion, I will be talking about topic 7 in conjunction with 3. With our known values of dP, the porosity, length, rho, and mu, we are able to solve this problem, which is an espresso machine extracts water through a coffee-packed bed by a pressure gradient. Now, we would like to find the Reynolds number and the superficial velocity. Using the properties given and assuming steady, incompressible flow, fully developed flow, no work, and the following equations of extended Bernoulli, Reynolds, permeability, and Darcy's law, we are able to solve this problem. Here, using Bernoulli, we are able to cancel out P1 and P2 over rho, because P1 and P2 are equivalent as they are both exposed to the atmosphere. We are also able to cancel out V1 because we are assuming it is so small compared to the velocity at point 2. In addition, we are able to cancel out point 2 because we are ignoring kinetic energy. Now, the friction factor we are able to solve now for the Bernoulli equation is equal to g minus the height difference at point 1 and point 2. We are then able to calculate the superficial velocity using Darcy's law, which we are then used to be able to calculate Reynolds number, with the following values as shown. For the next part, if the flow is laminar, we are asked to calculate the permeability. Because the Reynolds number is less than 10 with a value of 9.9, we are then able to use Darcy's law and the Reynolds number in order to calculate the permeability, with this equation shown. We are then able to determine that the permeability is 1202.9 Darcy's. Continuing on with topic 8, we are able to solve the following problem. A mischievous child decides to throw a jumbo-sized hot dog off the Empire State Building. The diameter is given of the circular area as 1 inch, and the density of the hot dog is given to be 1.033 grams per centimeters cubed. What is the terminal velocity the hot dog achieves? We are assuming that the CD is 0.5 for a laminar flow ellipsoid. We are given our known values as stated here. We are finding the terminal velocity using the properties from table A15, we're able to make the following assumptions in addition, which are incompressible air, no change in G, surrounding fluid is the air, therefore buoyant force is negligible, and no rotation of the hot dog in the air. Using the equations of the force of drag, weight force, and buoyant force, and the terminal velocity, we are able to solve this equation. We are able to do a force balance here, which we are then able to simplify for the force of drag for this following equation. We are able to plug in for the weight, and then we are able to plug in the volume equation. We are able to set these equal to each other and solve for the terminal velocity as shown, which can then be determined to be 22.38 meters per second. We're able to assume, again, that the buoyant force is negligible because the surrounding fluid is air. Continuing on with topic 9, we are able to discuss converging-diverging nozzles. They are often used in rocket engines and to produce high thrust output. A NASA Saturn V rocket is taking off with air moving into the nozzle at a temperature of 3600 Kelvin and a pressure of 5 MPa. We are to calculate the critical temperature, pressure, and density of the isentropic compressible air moving through the nozzle. We are then asked to calculate the velocity of the air exiting the nozzle. Here, using our knowns, we are finding these, as mentioned above, and our properties. We're able to make the assumptions that air is an ideal gas, steady flow, one-dimensional flow, and isentropic. Here, we have our critical isentropic air equations, and we are able to solve as such. We are able to solve for our initial density by dividing the pressure initially by R and T naught, which is our initial temperature. Here, we are then able to solve for our critical properties using the equations above in order to determine the critical temperature, pressure, and density to be 3000 Kelvin, 2.6 MPa, and 3.1 kilograms per meters cubed. For part B, for solving for the velocity, we're able to use the following equation that the Mach number is equal to the velocity over c. Here, we know at critical points the Mach number is equal to 1, therefore v is equal to c. Using that c is equal to the square root of kr times the critical temperature, we are able to determine that the velocity is 1100 meters per second. Last but not least, we will be talking about topics 10, 11, and 12. Here, we are relaxing on Blue Water Beach in Bear Lake, Utah, and you notice some kids skimboarding on a nearby puddle of water. It is 3 inches deep. The kids are using boards with a large width of 20 inches compared to the fluid depth and a length of 50 inches. Using a snapshot at the instantaneous moment of the board moving over the water, we are to determine the analytical velocity profile, the velocity at y equals 1 inch, the numerical velocity equations, and graph the two solution methods on Excel, and state the 3 boundary conditions and when they can be applied with supporting equations if applicable. Here we are shown of our knowns. We are finding and we are assuming Newtonian fluid, constant density, constant viscosity, no electric field, steady state, delta P is equal to 0, no slip at walls, Vy equals Vz, which is equal to 0, gravity acting downward, fully developed flow, and Vx is not a function of z. Here we are showing that the Cartesian continuity equations, the x component of incompressible Navier-Stokes, second derivative of numerical approximation equations. Here, starting out with continuity from handout 10, we are able to make simplifications because we are steady state, the velocity of y is equal to 0, and the velocity of z is equal to 0. We then end up with the partial derivative of Vx dx is equal to 0. Now, using the x momentum balance from handout 10, we're able to make additional simplifications. Again, we are 0 because of steady state here with velocity with respect to time. We are able to set the partial derivative of Vx dx to 0 because of continuity. Vy is equal to 0 because we only have fluid flow in the x direction. Vz is equal to 0, and delta P is equal to 0. In addition, the second derivative is also part of the continuity, which can then also be taken to be 0 because the first derivative is equal to 0. Then, because as stated in the problem, we are using a wide board compared to the depth, and x is not a function of z, we are able to set this equal to 0. In addition, gravity acting downward makes this term also go to 0. Now we end up with the partial second derivative of Vx dy is equal to 0. Taking the integral twice and applying our boundary conditions, we then end up with the velocity profile as shown here. Applying our boundary conditions, we are able to simplify further and get this velocity profile equation analytically. Moving on to part B, we are then able to find the velocity at y equals 1 inch. Plugging in, we are able to determine that v of the velocity x profile at 1 inch is 1.67 meters per second. Now, in order to determine the numerical velocity profile, we need to use finite differencing. From the known equation of the second derivative finite differencing, we are able to substitute, and we are able to determine the following equation here, with these same boundary conditions. Comparing the analytical and numerical solution, we are able to compare these on Excel from an Excel document that was created independently on my own. Here, you plug in your known values and you are comparing the analytical and numerical, which are shown by the red line and blue dots here. We are able to show that these are equivalent solving methods. For the last part, we are able to show that there is no slip at the solid-fluid interface. This can be used because of general fluid dynamics definitions. Symmetry can be used at the center of pipes, midplanes, etc. because of mere geometry, and continuous shear. This can be used at fluid-fluid interfaces or fluid-gas interfaces, as shown by the following supporting equations.